Yeah, Assalamualaikum and good morning. Hello everybody, welcome to module of process control. So this is a class for introduction to process control. So what we are going to know is that about the prototype system learning tank, what is feedback control, implementation of control, justification of control, which is why we have to do process control in this course. Okay, class. This is example of process control in our daily life. Okay, the person. What we are going to look is about the uh, shower with hot water supply and cold water supply, and this is a bath, and this is the shower. Okay. Okay. What is exactly happened in slide 2 just now is that this is what we are going to know what is a block diagram of shower control system. Okay, first there is a desired temperature set point. Okay, and there is temperature error and this decision delay. Okay, brain to muscle delay, this bath, temperature at missing point, and this flow delay, and then temperature at toe or finger. Okay, this is what we call block diagram for the shower control system. Okay, this example what is like for the home heating control system. Okay, in Malaysia we didn't have this thing. It's because we don't have four season. This is mostly for the country with four season, especially for the winter. So this is what happening for the home heating control system. Next, for you to understand in this course is that we must understand what is the control terminology that we are going to use. Firstly, what you mean with control variables. What is meant by manipulated variables and what is meant with the disturbance variables. So if you can see the definition for control variables is that any variables which quantify the performance or quality of the final product, which are also called output variables. And what is manipulated variables? These input variables are adjusted dynamically to keep the control variables at their set points. And another important variables or control terminology that you must know is about disturbance variables. These are also called load variables and represent input variables that can cause the control variables to deviate from their respective set points. So after we learn about the control terminology, these are some typical continuous process that need a process control, such as heat exchanger, where there is cooling medium and process fluid. Second is a chemical. Second is a chemical reactor. Okay, where there's a reactants, cooling medium, cooling out, and the products. And for another type of continuous processes is cracking furnace. If we do is a crude oil, fuel plus air, cracker products and combustion products, and a distillation column. Okay, distillation column, we got a feed, distillate and bottoms. So these are example of typical continuous process. The next thing that we must know what is another process after continuous is the typical operation with each non-continuous, or we call it batch process. So for example, semi-batch reactor where there is a feed, there is cooling medium, and we got also wood chip digester and we got the plasma ether, and we got some example of uh, not in a unit operation but in a typical in our daily life, okay, such as kidney dialysis unit, where we got pure blood, dialysis medium, and purified blood. Okay. Another control terminology that you must know is about the set point change and disturbance change. And in process control, the performance of process is basically we look for the set point change and disturbance change. Okay, set point change meaning that implementing a change in the operating condition. So the set point signal is changed and the manipulated variable is adjusted appropriately to achieve the new operating condition, also called servo mechanism or servo control. Another terminology is about the disturbance change. In other words, how your process will come to steady state after we introduce disturbance variables to the process. Okay, so in another words, disturbance change is the process transient behavior when a disturbance enters, also called regulatory control or load change. So a good control system should be able to return each control variable back to its set point. So this is two important thing when we do process control, the performance of our unit operation or for the whole system. So we look for the example for the stir blending system where we got a mixture of A and B, and then we got a pure A, and then this is the output where W1 and W2 and W are mass flow rates, whereas X1, X2 and X are mass fraction of components A. So this is the valve, so this is the impeller. One more thing that important when we are doing process control is that we must always make an assumptions. And in this case, we are going to develop a model for uh, the blended system. So there's three assumptions. The first one is W1 is constant. The second one is X2 is constant and equals to 1, since stream 2 is pure A. And the third assumption is that a perfect mixing in the tank. So what is our control objective in this system is that we want to keep X at a desired value, or we call it set point. So the notation that we are going to use is XSP. Okay, despite variation in S1T, so flow rate W2 can be adjusted for this purpose. So terminology that we are going to use in this example is that control variable or output variable X, the manipulated variables or input variable W2. So the disturbance in this system in the example is the load variable, which is X1. The next step is that what value of W2 is required to have the X equals to X set point. So the first thing that we have to do is do the overall balance, okay, which is W1 plus W2 minus W, okay, and we name it as the first equation, and then we go for the component balance. Since we have only A balance, we have A and B, so we go for component A balance. Okay. So for A balance, W1 times X1 plus W2 X2 minus WX equals to 0. So the over bars denote the nominal steady state design value. So at the design condition, we got X bar equals to X set point. So substitute equation 1 to X bar equals to X set point and X bar 2 equals to 1. Then we solve equation 1 to this one to find what is the value of X2. Then we got this is type of equation for the W2 and we name this the whole equation as equation 3. So equation 1, 3 in slide 10 is the design equation for the Dendry system. And if our assumptions are correct, then this value of W2 bar will keep X bar at X6 points. Okay, so what if condition change? So the control question is that suppose that the inlet concentration X1 change with time. How can we measure that X remain at or near the set point XP? So this case is example of disturbance, the terminology that we use when we introduce disturbance to the system. So disturbance in this example is the inlet concentration. Okay. So as a specific example, if x1 greater than x1 bar and w2 is equal to w2 bar, then s will be greater than x set point. So we have to change a control strategy. Method 1, we measure x and we adjust w2. And then we continue, we change also from manual control to automatic control and also proportional feedback control law, which we got, we name it as equation 4. So what is KC? KC is called the controller gain and W2 X2 denote variables that change with time. And the change in the flow rate is proportional to deviation from the set point. Okay, if we choose method number 1, so we will change, we have to put the composition controller, composition analyzer transmitter, which the symbol AT, capital A and capital T, and composition controller is capital A and capital C. And the dotted line is represent electrical signal in our blending system. Okay, so if you notice, figure 1.4 is different from the previous figure because in this case we got we have to change x2, so we must measure the composition controller with installation of composition transmitter and composition controller. So it's quite different from the previous figure. So this figure is different from figure 1.4, which in this figure we are going to choose control method 2, where we put the composition controller and composition analyzer at streamline x1 and the control valve by adjusting the input from x2 equals to 1. So method 3 is measure x1 and x2 and we adjust W2. And finally method 4 is we use a larger tank. If a larger tank is used, fluctuation in x1 will tend to damp out due to the larger capacitance of the tank contents. Okay, however, a larger term means an increase of capital cost. So this slide just to give a negative feedback and positive feedback, advantages and disadvantages. And this one is about feedforward control. Another type of terminology that we are going to come in this course. Before this, we call it feedback control. This one is about the feedforward control. And the advantage is that correct for disturbance before it upsets or um, it upset the process, or we call it the performance of your system has been delayed. The disadvantages is that it must be able to measure the disturbance and no corrective action for unmeasured disturbance. So what we are going to this is an example of a implementation of process control in daily life. So the example of closed loop artificial pancreas. Okay, and closed loop is another example, terminology that we are going to use a lot in our course. Okay, for this process control. So what is look like? What is the block diagram? We call the whole thing is a block diagram. So we got a glucose set point, and this one is our controller, and this is the pump, which we call the whole process, and we got a sensor. So this one is the measurement, this one is the process U, R represent the set point. Okay, so feedback control, closed loop, we got the measurement from the output. Okay, we go back to our set point, our reference, and remember that in process control we always using the error. So based on the error from the set point and the measurement, it goes back to the system and it will determine if it is enough insulin pump to the patient. Okay, so this is another example of the feedback control system, and we call the whole thing is a schematic diagram of temperature feedback control system for a stirred tank heater. Okay, and remember that the dotted line is for the electrical instrument line. Okay, TT stand for temperature transmitted, capital TT, and capital T and C stand for temperature controller. Okay, in process control, the first thing is that you must know how to draw the schematic diagram. The next thing is that you must draw how to do block diagram for temperature feedback control system. So what it look like is that the whole term we call it block diagram. Okay. So the calculation performed by controller is this thing. Thermocouple calibration, comparator means the set point and the measurement, the current measurement, and this is the controller. It will goes to the heater, and then it gives the Q, and then it goes for our unit operation. In this case is the stirred tank. Okay, and this is the value that we are going to use in stirred tank, and this is the output from the stirred tank, and it will goes for this system for the closed loop, and then it goes back to the set point, whether it's in line with the set point or is it increase or decrease. Okay, so the whole two things that you must remember is about this, how to draw schematic diagram And what is about the block diagram for, in this case, temperature feedback control system. And then we come to the justification why we do process control. Okay, so there's a 1, 2, 3, 4, 5, 6, 7, 8, 9. In general, there's specific object, 9 objective of control, but the first thing is that it's all about safety. So we want to increase or we want to enhance process safety. Okay, and then we want to increase product throughput, increase the yield, and this about the decrease the energy consumption, decrease pollution, is about the environment. Okay, decrease of spec product, this about the quality, which we can conclude for these two. It's all about the product, and we can say it: decrease of spec products, increase product throughput, and increase yield of higher value product is, we can combine it for the products. Okay, and then we want to extend our life of equipment, because our unit operation is not cheap, so we must uh, do very good maintenance for the unit operation. And the next thing is, we want to improve the operability of the unit operation, and we want to decrease the production labor. That's why we go for the automatic control. So this justification why we have to do process control in a unit operation and for the whole system. So the next thing is that what is the hierarchy of process control activities? Okay, the first thing is that measurement and actuation, which always less than 1 second, and then safety, environment and equipment protection, and then we go for regulatory control. The next step is multi-variable and constraint control. The next step is that real-time optimization, and then it's go for the planning and scheduling. So all these things is a two-way operation, and we call it as a hierarchy of process control. Figure 1.110 is major step in control system development. First thing is the control objective. Okay, the engineering activities is in a oval shape, and for information base is a triangular shape. Okay, so we got information from existing plants, if able, or maybe from our design, and then we formulate our control objective, and this management objective. The next step after we formulate our control objective is that we develop process model. In order to develop process model, we got data from physical and chemical principle, and then we also get the data from plant data if available, or it can be computer simulation. After we develop a process model, we go to device control strategy. So device control strategy, there's two ways: computer simulation, and we got the data from process control theory, and also experiment with existing plants. Okay, after we develop our control strategy, the next step is that we select control hardware and software, and we got information from vendor. The next step is that we install control system, and then we adjust controller setting. Okay, install control system. That's why we call it control and monitoring. We do control first. After that, we do monitoring. Okay, so in monitoring, we adjust controller setting. So we got the final control system. So this is basically major step in order for us to develop the whole system. Okay. This model is can be from first principle, or it can be from empirical model, which means we got it from experiment or from plant data, and we got the equation and we develop for the process model. Okay, that's all for chapter 1, and our next is our activity, which I will give quiz using Kahoot. So you can recall back what we have studied in this chapter 1 before we proceed with our quiz, and later on we'll proceed with our next chapter. Okay, and then there's some short assessment in order uh, to measure how much you understand from this chapter 1 and the next chapter. Okay, thank you. So we take a short break. We'll follow with our activity. Thank you.